Section 11.4, phase changes. Phases, of course, are solid, liquid, and gas here on Earth for the most part. And we need to know the names of the changes between these. And then after we take a look at those, we'll look at the energetics of those phase changes based on the molecular structure. So first of all, when you go from solid to liquid, or liquid to solid, the names are melting, or sometimes called fusing or fusion, confusingly. Freezing, liquid to solid, sometimes that's also termed as fusion or fusing together of liquid to solid molecules. Vaporization, going from liquid to gas. Condensation, going from gas to liquid. Sublimation, going from solid directly to a gas. And deposition, going directly from a gas to a solid. You can look at this diagram, figure 11.20, and you can see the names of the changes, red and blue, different colors, and where they go from solid to liquid to gas. Notice the larger space here between liquid and gas, because solid and liquid are generally called the condensed phases of matter, because the molecules are closer together. So each one of these phase changes that we've named right here is accompanied by a change in energy. And the changing energy, a triangle E, or at constant pressure a triangle H, or delta H, has a specific name for it as well. When you go from liquid to gas, it has an enthalpy or a heat or an energy of vaporization. From solid to liquid, or vice versa, liquid to solid or gas to liquid. Anyway, this is called the enthalpy of fusion, the solid to liquid change. And there's an amount of energy associated with it based on what the substance is. So for example, from solid to liquid water, it takes an amount of energy of 60.01 kilojoules to move 1 mole of solid water to liquid water. For a change from liquid to gas, vaporization, liquid to gas right here, it takes an enthalpy of vaporization of 40.7 kilojoules per mole of water moving from liquid to gas. Notice how this one is like 6 times, almost 7 times as much going from liquid to gas. And that's because our liquid to gas phase change has to separate the molecules so much more, because liquid and solid are, so much closer together, gas particle-wise. It just takes a lot more energy to go from the liquid to the gaseous phase, because the gaseous phase is so far apart. So let's take a look at this figure right here. You can see the heat of fusions and the heat of vaporizations and the heat of sublimation, which is the addition of the two. So let's take a little closer. Heat is on the vertical axis right here in kilojoules per mole. Just take a look at water. Water is about 6 kilojoules per mole for the heat of fusion, and then about 41 almost for the heat of vaporization. And then if you add those two together, that would be the heat of sublimation. You can see mercuries are a little bit bigger. You can see some other examples here in diethyl ether and butane right here. But for all of them, you'll notice the smallest one is from solid to liquid. And of course the biggest one is the addition of the two. But the heat of vaporization is always much larger because you're going from a liquid to a gas. Well, we can draw this as a heating curve, or a curve diagram of energy versus temperature. And this type of picture right here is what we're going to draw on figure 11.22. And you can see this heating curve right here shows temperature in degrees Celsius on the vertical axis right here, degrees C. And it goes from -25 Celsius all the way up to 125. And then on a horizontal axis is the amount of heat added. Heat added in kilojoules, heat added as enthalpy, positive delta H right here, because you have to put energy into the system to heat it up. This shows that when we move from this heating curve happens to be for H2O, okay, from solid to liquid to gas. And this is the solid phase of matter right here. This is where it melts and goes from solid to liquid. And so there's an enthalpy, a heat amount, and this would be like 6 kilojoules per mole. And then from here to here, we're going in the liquid phase and heating it up from 0 up to 100. And that at 100, we go from liquid to gaseous phase. We boil it right there, or we move it, vaporize it, I should say. And remember, that's about 41 or so kilojoules per mole. And then we heat it from there even higher, from 100 to 125. And so this is in the gaseous phase right here. Well, we can use this idea of a heating curve right here to calculate the amount of energy it takes to change a substance from solid to liquid to gas based on how many phase changes it goes through. And sample exercise 11.13, we're going to go through that right now. So it says calculate the enthalpy change upon converting 1 mole of ice at negative 25, right here, negative 25, to steam at 125, right here. Under a constant pressure of 1 atmosphere, the specific heats of ice, liquid, and water and steam are 2, 4, and 1.8 respectively. And then they give us the enthalpy of fusion, and they give us the enthalpy of vaporization right here. So why did they give those specific heat capacities? Well, we learned about those way back in chapter 5. And if we have a change in temperature occurring, like right here, or right here, or right here, we have to use the MC delta T equation to calculate the change in energy. So this is where we're going to use M times C times delta T for each one of these. And then at each one of these phase change points right here, this is where we're going to use the enthalpy of fusion, delta HF, or the enthalpy of vaporization to do that phase change type energy. So it's actually 5 different equations that we're going to use, and then we'll add them all together to find the total enthalpy in the end. So let's start with negative 25 up to 0. And for this, we need to use the equation M times C times delta T. And the mass is 1 mole, it says. And in 1 mole of water, there's 18 grams. You add it up on the periodic table, so 18 grams. And then times the specific heat capacity, or C, of ice. So we want ice right here, and that's 2.03. So 2.03, and that's in joules per gram degrees Celsius. And then we're going to heat it from negative 25 up to 0. So that's a 25 degrees Celsius change. Then at 0 degrees Celsius, this is where we're going to melt it. And at this point, notice, before I go on to that, notice the Celsiuses cancel and the grams cancel. And so my answer is going to end up being in joules for this part right here. Okay, at 0, we're going to do the melting. And now we're going to take and since we know that we have 1 mole of the substance, and we know that for every 1 mole it takes, this is given to us right here, 6.01 kilojoules per mole, we can multiply those guys together, and we know that the amount of energy that it's going to take just to melt it at 0 without changing any temperature is 6.01 kilojoules. So notice this one's in kilojoules right here, the second one. Okay, then our third one is from 0 up to 100, 0 to 100. And here we're going to use MC delta T again, M times C times delta T. And the mass, once again, is 18 grams because we still have 1 mole of water. And this time, the specific heat capacity is 4.184, which we learned this number back in chapter 5. And this is in joules per gram degrees Celsius. And then that's 100 degrees Celsius that we're going to change it. Once again, our answer will be in joules for that one. Then at 100 degrees Celsius, that's where we're going to boil it, or we're going to change it from liquid to gas. And so this is where we're once again going to use 1 mole, and then we're going to need that enthalpy of vaporization, which is 40.67 kilojoules per mole. So notice how my moles cancel with my moles once again, and I'm given a kilojoules answer for this part. So notice how they're in different units here, and I'll have to convert those before I add them all together. And lastly, we're going to go from 100 to 125 degrees Celsius, from here to here. And once again, we use M times C times delta T. Mass, once again, is 18 grams because we haven't changed the amount that we have. But the C changes because here is our enthalpy, our specific heat capacity of vaporized water, 1.84, and that's once again in joules per gram degrees Celsius. And then we're going to multiply it by our change in temperature, which is 100 to 125, so 25 degrees C is going to cancel right there. The Celsius cancels with the Celsius, the grams with the grams, and once again I'm given joules. So now I'm going to have 5 different enthalpy changes. I can add those all together, and the total amount of enthalpy, or the total amount of energy that's going to be needed to raise it from negative 125 all the way up to steam then would be the addition of all these parts. And I'm just going to leave this up on the screen here, and you can copy them down if you want, but this is I believe, let's see, 910 kilojoules. This one would be 6 kilojoules. This one would be 7,500 joules. And see how they've converted it to kilojoules already. This one's 40.7 kilojoules, and then this one would have been 830 joules, or 0.83 kilojoules. And when you add all those together, we get about 56.0 kilojoules that are going to be needed to raise and change that temperature. All right, last piece of this is some critical pieces in these changing areas right here. And these are just 2 definitions. These 2 definitions have to do with when we arrive at this point where you're a gas, and you should be able to change that gas to a liquid if you compress it enough. Well, eventually you get to this point where no matter how much you pressurize and push the particles together, you can't change it from from gas back to liquid. And this point is called the critical temperature and the critical pressure. And so the critical temperature is the highest temperature at which liquid phase exists, and then the critical pressure is the pressure required to liquefy a substance at that critical temperature. And we'll come back and revisit these when we get to phase diagrams in a little while. But knowing that these pieces are associated with energy, and that it takes a certain amount of energy to get them to this point, and then you can't liquefy them anymore, is kind of a neat piece. So critical temperature and pressure are the last pieces of this section. And so today you should have learned something about critical temperature and pressure. And here are critical temperatures and pressures of various different substances. And here's water and ammonia. Notice those are really high critical temperature and pressures because they have hydrogen bonding. Compared to other things. You should have learned something about heating curves right here, and how heating curves describe how things go through the solid to liquid and the liquid to gaseous phase. And then you should have learned something about enthalpies of fusion and enthalpies of vaporization, and how those energies are associated with phase changes.